Bismillahirrahmanirrahim. Assalamu alaikum dear students, welcome back in lecture 10. Student, basically is in lecture number 9 we covered that example which we start from lecture number 3. But remember, this is very important to share this information with you people, that for that example, okay, this is another example, but as in that example which is we did in lecture from lecture number 3 to lecture number 9, we analyze only the interior frame. Okay, so you have to analyze one exterior frame in east-west direction as well, and similarly one interior frame in north-south direction and one exterior frame in the north-south direction. That will basically complete your whole calculation for that frame system. So you have to run four analysis, okay, and that then you will complete the analysis. Okay, but remember, if you are going to design, because somebody questioning about the design of the columns, so in the column, basically as we did analysis in the east-west direction, we got movements right here, but when you did analysis in the north-south direction, you also got some movement here. So if let's say this is my y-axis and this is my x-axis, so you got movement about x-axis and movement about y-axis, and similarly you got the loading, okay, the total load which is coming from this side beam and similarly from this side beam and as well as from this one. So adding these three beams reactions over this column, then you will, so you have movement mux, muy, as I explained in lecture number 7, I think so. So please go there and watch that lecture. So after that you will be able to design this column and this column. Clear? Now in this lecture we will cover this example very quickly. I have to explain thoroughly all concepts, all steps of the equivalent frame method from lecture number 1 to lecture number 9. So please watch those lectures sequentially, and if you have any ambiguity regarding those lectures at any steps, you can ask question through comment box. Clear? And in this lecture, basically what I mean from this lecture, that I want to share you when you will you people face any kind of asymmetric plane, or you can say unsymmetric plane system or structure like this one. You see in x direction it is unsymmetrical, but in y direction it is symmetrical. And one thing which is very important to share with you, one best example, okay, that let me show you that picture, right, this one. This is very important if you people face this kind of problem, okay, because most of the student when facing such kind of problems, they can't able to do such kind of analysis for such kind of structure. So you see there, this is a north-south direction strip, clear, interior frame which they are basically showing you, and similarly in east-west direction this is the interior frame. Now this is the width, okay, that is L2, and here you have L2, and similarly you have C column, shear walls. Now remember, shear walls, now it acts like a column, okay, and remember there are some limitations in DDM method, although this is a flat slab system. And in DDM method, let me show you those limitations. Clear? This one, you see equivalent frame method and DDM method comparison according to the limitations as applicable in the ACI 31814 edition. So you see these are the limitations of the DDM method, but there are such limitations which is not applicable, or you can say which is not applicable in the equivalent frame method. The one most important limitation is this one: column offset shall not exceed 10%. I already explained this in my those lectures which I have uploaded in the DDM method. Basically, if you go to visit my YouTube channel, there is a full playlist regarding a DDM method. I explain thoroughly these limitations, so please go there and watch these limitations. What does it mean? But if there is no limitation, for example, let me show you here. For example, you have one column here, one column here, okay, and the other column here, but this column is not in line with the center line of these two columns. It is okay, this is the center line, so there must be, this column should not be more than 10% offset from this center line. Now what does it mean? Please go there and watch what does the limitation mean. But this kind of limitation is not applicable in the equivalent frame method. Okay, there is no such kind of limitations. So this is one of the beauty of, you can say, the equivalent frame method. Clear? And you see that limitation right here in this. You see the columns are basically if you draw a line over here, so you see this column is offset. Okay, so here basically DDM method is not applicable. You have to apply your equivalent frame method. Clear? So this is very interesting, okay, to share with you this kind of examples. You people must face this kind of difficulties, okay, and these limitations, okay, these limitations are very important. Okay, what remember, concentrated load in DDM method is not allowed, but it can be permitted in the equivalent frame method. Okay, similarly openings in both method is not applicable, and unbalanced movement, this is a fast and this is a limited. It is you already see the drawbacks of both methods, and all these are the comparison of DDM in equivalent frame method. Clear? Now we will start our example right now. Clear? So this is the example. You see that we have two columns. This is 12 by 20 column and this is 12 by 20 column. I already did this example, okay, in my lecture number 2. If you visit that lecture number 2, you see this example I already shared with you people. And here we have one exterior column and one interior column, and I already did the calculation for C, KT, okay, and similarly what is LC, LU, and how to calculate your KT values, how to interpolate the values from table A17, table A14. I already explained. So here I am not going to explain these steps. You have to go to my lecture number 2, okay, in equivalent frame method, and where you will find this lecture where I explain thoroughly these steps. Okay, now this is the example. Okay, let me discuss it. Okay, you see the same figure right here, and here things are interesting because you see here is C1 is 12 inch while C2 is 20 inch. Here C1 is 20 inch and C2 is 12 inch. Okay, so this is because the orientation of the column is changed. L2 is half from this center line to the center line of this column and half this one. But here A2 and B2 span is different as from B2 and C2 column span. Clear? So we will separately calculate all the things. K is B will be determined from this panel as well as for this panel. Okay, in our previous example, case B for this panel is same for the rest of the panels. Clear? So this is the difference. Now this is the example, and this is the data. Okay, I already shared this in lecture number 2, so please go there and watch lecture number 2. Okay, I already explained these steps, how to interpolate. I already explained this. Now this is important. You have to interpolate these values from table F14. Let me share table F14. Here you see table F14. I already explained this in lecture number 3 and 4, I think so. So please, you have to watch those lectures. This is table F14, and from here you will got M, K and carry over factor values for your K is B determination. What is K is B here? So KEL2, okay, KEIS divided by LC, okay, that is the clear length. And you have to find C2L2 ratio, C1L1 ratio, and just pick the value from this table and plug that k value here, you will got your k is b. Clear? And okay, they basically interpolated all these values. So watch lecture number 5, 6, I think so, where I explain the whole procedure. Now for you have to calculate k is b for span A2B2 and B2C2. Clear? So you see the procedure. In case of B2C2, we have C120. I already explained it. And you have to find C1L1, C2L2, go to table F14, interpolate the values as you did here. Clear? And this is your moment of inertia of slab, 189. 189 is what? Okay, this is this length. This is L2. 15 feet and 9 inch, I think so. This is 189, sorry. Times 7 cube divided by 12. Here, KA2B2, okay, this is K is B for 104 and B2C2 is 76.9. Okay, so B2, remember C2B2, K is B, the value this one will be same for B2C2 and C2D2. Clear? Now, the next step is you have to calculate your C value. So I already explained this in lecture number 2. Clear? So I'm not going to explain it. Similarly, these steps I already explained this in lecture number 2. So I'm not going to explain. This one is important. You have to find out distribution factor for A2B2 span. How to calculate it? KSB of A2B2 divided by KSB of A2B2 plus KEC of A2. Okay, if you are going to calculate your moment distribution factor for this point, so as here you have a column, clear? So that why you have to pick the KSB of this AB span divide by the KSB of this span divide by the KSB of this column. Clear? And so you see here they just picked the values and they did the calculation. They got 0.566. okay, 0.566. and for column A2 column, that is this one, this column, they got the value of, you see, 79.9 divided by 104. okay, let me show you the figure. This is the figure. You see, for this column distribution factor will be the KEC of this column divided by the KEC of this column plus the KSB of this column, that is 104. okay, and similarly for B2, okay, B2A2 span, your distribution factor will be 104 divided by 104 plus 161 plus 76.9. Similarly, for this column, your distribution factor will be 161 divided by 161 plus 104 divided by 76.9. Similarly, for B2C2, your distribution factor will be 76.9 divided by 76.9 plus 161 plus 104. Okay. This is the procedure how to find out distribution factor for your interior panels. Now the diagram is not clear, so here I will show you the diagram. This is the diagram. This is very important, the cantilever portion. Remember, this is the cantilever portion, because if you see this figure, you see here that here you see from the center line the slab is cantilevered a little bit. It is cantilevered, and you see here it is 4 inch, okay, cantilevered. So that why we have to run the analysis for that cantilever portion as well. But as the moment is not transparent to the cantilever portion, so that why its values will be taken as 0. You see here all the things are 0. okay, and the 0.566 is the distribution factor for A2B2, and this 104 is the KSB for this A2B2, and this is carryover factor. This is taken from table F14, I think so. And similarly for B2, okay, the distribution factor is this one, and yes, the distribution factor is this one. Similarly, for this column, this is the KEC value, this is the carryover factor, and this is the distribution factor. Clear? For this A2 column, we will plug all these data into our moment distribution table. You will see, and this is the cantilever portion. All the things are 0 for this cantilever portion. Okay, now the rest of the things are same. Yes, you see here the cantilever portion is okay, it is projected, and we will account this in our moment distribution table. Now here you see loading cases, so where we have to run the pattern loading or not. So as you see, your live load is 40 psf, which is less than 3/4 of QD, that is the dead load, that is 84 point. So 40 is less than 84, so that's why we don't need to run the pattern loading. We just consider the full factored live load and full factored dead load. Clear? As we did in lecture number 8. Clear? So this is our QU calculation. Total factor load 1.2 of dead load, 25 is the superimposed dead load, and 1.6 is the live load, and our L2 is 15.75 feet, and this is our M, the fixed in moment. Remember, 0.084 is taken from the table. Remember, it should be 0.084 is taken from the table A14. It is interpolated as we did for example number 1. Clear? And you have to multiply this QU, that is 0.199. L2 is this one, and L1 for a 2B2 span, you see here, that is 17 feet and 9 inch. But that fixed in moment will be only applicable in this span. Now for this span, you have to determine again fixed in moment, because here this thing is changed. Clear? And the rest of the things are same. Clear? Now this is important. As you see in this figure, this cantilever portion, but at this cantilever portion we have a wall right here. Clear? You already see that there is a partition wall. In many buildings people may experience that at the cantilever portion there will be a wall, okay, or in some cases there are bathrooms, okay, or washrooms, etc. walls are present. So this is, let's say, this is projected 4 inch, okay, and there is a column face, okay. So let me explain this scenario, okay. Assuming 300 pound per feet loading of the wall, this is assumed, okay. You can find the thickness of the wall that you will see here, and the height of the wall with multiply with 1 feet, okay. So you got the wall weight per feet. So but we assume this 300. Now you see here, this is the column face, and the slab is projecting for a distance of 4 inch. Clear? The total distance from the center line of the column, because this column is, remember, there are two the column which is right here, you see this is 12 inch, and it is projected for a distance of 4 inch. So 12 divided by 2, you got 6 inch, okay. So this point must be clear. Now you see 6 inch is the face of the column, plus 4 inch, you got your distance 10 inch. But 10 inch is up to the face of the wall. You have to find out the center line of the wall, because the load of the wall should act at the center, okay, at the mid of the wall. So here the total distance is 8 inch. From the center line of the column to the center line of the wall, the total distance is 8 inch. This step should be clear. Now, what will be the weight of this wall? You see 1.2 times 0.30, that is the load of the wall, times 15.75, because this wall is over this distance. So that's why they multiply 15.79, okay. The length of the wall will be this much. So once you multiplied 0.30 with this length, you got the total weight of that wall. okay. And next, times 8 divided by 12. Okay, 8 is the thickness of the wall. Okay, 8 inches is the thickness of the wall. So you got 3.78 kip movement. Remember, this is movement. Okay, 8 inch, sorry, it is not the thickness of the wall, it is this distance. So it is movement arm. Clear? It is movement arm because this wall causing a movement. Okay, this wall causing a movement. So you got 3.78 kip movement due to wall. Now as you see this slab portion, so this slab portion will also tend a movement right here. So that way we have to find out the movement of this cantilever slab as well. And how to find it? You see the calculation for that slab portion. 1.2 is the factor, 15.75 is the length of the slab, and 7 inch is the thickness of the slab portion divided by 12 times 0. This density, and this is total distance is from, because you have to count from the center line of the column. Okay, so that's why we are getting 10 inch. So 10 divided by 12 times the half of the 10. So you see, so we got 0.57 kip feet. This is the movement, remember. This is the movement of this projecting slab. And you have to add this with the wall movement. You got 4.35 kip, which is around about 4 kip feet. Okay, so this is the movement which is caused by this projecting portion at the center line of the wall, and it will be a fixed in movement, you can say. Okay, it will be acting as a fixed in movement. So after that you have to draw your moment distribution table. You see A2, B2, C2, D2 are the points. Okay, let me show you this one. A2, B2, C2, D2, and then the carryover factor, and this is the cantilever portion because for this distribution factor is 0. Clear? And this is the distribution factor for A2 column. This is the distribution factor for A2 B2 span. This is the distribution factor for B2 A2 span, and this is the distribution factor for B2 column. And I already explained these values. Okay, you see 0.82 column distribution factor is this one. Distribution factor for this cantilever is 0. Distribution factor for A2 B2 is this one. Clear? So these steps are simple. Then you have to show the fixed in movement. Now you see this cantilever portion, basically you see here it causing a movement. Okay, and here basically this portion at this joint we have to balance that. This movement is around about 4 kip feet, so we have to, there will be a fixed in movement at this joint for this cantilever portion, so that movement will be 4. Now you see this movement is positive, but this one will be showing as negative. Similarly, we have a movement right here, that is the fixed in movement we already determined for A2 B2 from formula. This will be denoted with positive, but this movement will be denoted with negative sign. Clear? Similarly for all the rest of the spans. So the column, we don't consider this movement. This is the movement for the A2 B2 span, and this is the movement for B2 A2 span. Clear? It is important. And A2 B2, let me show you this value where we calculated this one. You see here 82.9. This is the fixed in movement for A2 B2 span. And yes. Now next is 105. 105, because in the same formula you have to use the same formula, but in this formula L2 is fixed but L1 is changed. Here you have to plug 20 feet, not 17.75 for B2 C2 span. Clear? Because this is an unsymmetrical case. The next thing, all the values you just plug. Okay, this portion, now remember this is very important. Clear? Let me show you here. Remember there the movement is in this direction, so that why in that joint, that is D2, we have to consider it +4, but here we will consider as at A2 we will consider as -4. Clear? Now you have to run the moment distribution table, okay, as we run in the case of our moment distribution table in the case of example number 1 as we did. Okay, let me show you. I think so I run this table here, but I think so this is not this one. Okay, no. Okay, but you can do the same calculation in this kind of loading pattern if you have this kind of table. So you have A, B, C, D joints, and you have a UDL loading, and you have fixed end movements. Okay, so this is a simple procedure. You can run this table, and this table is also available in the McGregor book. Okay, if you visit this here, you see this table which they basically did. Clear? So finally what movement we got. Okay, let me share those movements. Finally we got these movements, right? See, you see here -4, -36, 36. Okay, these are the final movements after the movement distribution table. Now you have to assign now these movements to the beam, to the slab. Okay, and as we did all these steps in our lecture number, I think so in lecture number 6, 7. So please go there, how to calculate, how to draw shear force diagram, how to calculate reactions, and the rest of the things. Clear? So let me show you some points here. Right here you see -4. This movement is at joint A2. So this is -4 because this -4 means this is a clockwise movement. So we show this with this direction, and from where this 5.67 comes, this 5.67 comes from the movement from the load. This is the load of the wall. I already show here 5.67. Clear? And you see from the face of the column this is 4 inch, but from the center of the column it is 10 inch. Clear? And remember, this is very important, this black color you see here, this is the UDL loading of the projecting slab, and that loading is 0.57, not this one. Okay, you have to find out by just 1.2 times 15.75 times 7 by 12, or 1.2 times 7 by 12 times 0.515. Clear? So you will find that movement as that UDL, because there the UDL is different and here the UDL is different. You see 3.134, we already calculated this value. Clear? This is this one, and yes, you have to multiply this one value will be this black one value 1.2 times 15.75 times 7 by 12 times 0.15. Okay, and you have to note this one. So you got the UDL loading for the cantilever portion, and after that you have to draw the shear force diagram. As this is a point load, so that's why it will causing this kind of shear right here, and then it will come to at the center line of the column, it will be 7.1. Clear? So 7.1 is equals to how they got this one. Okay, so it will be 5.67 plus this UDL, okay, times this distance, that is 10 inch. Okay, so you got 7.1, and similarly you see here 7.1 kif is the reaction for that cantilever portion, and 27.82 is the reaction due to the 3.134 times 17.75. Okay, 17.75 divided by 2. So this is the reaction due to this UDL loading. Okay, and this is the reaction due to these fixed end movements, are these support movements. You see 36 and minus 106, so it will causing to rotate this panel in this direction, clockwise direction. So to bring this panel in equilibrium, you have to apply an anti-clockwise movement, and that movement will be equals to this 3.94 times this distance. Okay, that can be balanced. So 3.94 is 36 minus 106 divided by the span length, that is 17.75. You got this value, and this will be in downward direction, this will be in upward direction. So I explained all these steps in lecture number 6, 7 I think. So please go there and watch those videos. Now finally you draw the shear force diagram. You have to find out the fast movements. How to find the fast movements? You see, this is the net shear force, 7.1 plus 27.82 minus this one. Yeah, no, 27.82 minus 3.94. Clear? You got 23.9. So after, because this 7.1 is the reaction for the cantilever portion. Now as the phase distance is 6 inch, so 23.9 minus, this is minus, okay, this is minus, this is not multiplication sign, this is minus the UDL times 6 divided by 12. Okay, so you got 22.33. okay, this is the fast movement. And similarly this one, and similarly you have to find all these shears. So I explained these points in my lecture number 6, 7. okay, so please go there. And now from this shear force diagram we have to draw our moment diagram. Okay, so here we have, okay, I draw the moment diagram from that shear force diagram. Clear? And remember, this is -4, you already know this is from the moment distribution table. -36 we already know from the moment distribution table. And the fast movement is -24.4. How I got this? You see the procedure. Okay, you see the procedure. Now this 23.9 plus 22, this is the shear area. Okay, this is the shear area for that portion. Okay, this is a trapezoid, so find out the area and multiply it with that distance, that is 6 inch. You got the shear area, subtract that area from this center line movement, you got this one, so that is 24.4. and similarly here you see you have to find out that shear area, this one. How to find this one? This shear area 29.2 plus 31.8 divided by 2 times this 6 inch distance. You got the shear area, subtract the shear area from this moment. Okay, you got the fast moment, that is 80.6. okay, so follow the same procedure, find out all these fast movements. Okay, and how I got this 55.1? So 55.1 is basically I think so, this is basically the you have to find out what you have to find out this distance. Okay, you have to find out this distance, okay, as we did in lecture number 6, 7. And then once you find out that distance, then using the moment equation you will find the med moment. Clear? So this is simple, how to find the positive moments. Now there are another checks. These checks are very important. All the rest of the steps are simple. Okay, therefore I'm not explaining these steps because I already explained, but this step is very important. Checking ACI section 13.6.1. basically this section, ACI section, explained that when you have to analyze such slab system which fulfill the requirements of DDM, okay, direct design method, and you are going to analyze that plane system, slab system by equivalent frame method. So this section says that m0, once you calculating, okay, m0 in DDM method we basically calculate the static movement. So the slab which fulfill the limitation of DDM, the total movement between faces of column can be reduced to m naught, as this slab satisfies the limitation of DDM. So this means that these face movement 24.4 and 80.6, okay, these movements can be reduced, can be reduced up to m naught. This says that these movements should not be more than m naught. How to do this step? Let's see. Total movement at the face of the column, this one and this one. Now 24.4 plus 80.6 divided by 2 plus 55.1, that is the mid value, positive one. Clear? You got 108 cap feet. This one should be less than m naught. So you already know m naught is QUL2ln square divided by 8, you got 106. So this is a little bit, or you can say this is close to this one. So no adjustment. We don't make any adjustment. Now we checking for B2C2 span. So here you see we taken the average of these two face movements. But here already these movements are same. So don't taking any average. You just consider 80 plus this movement and it equals to 131. But the static moment for this span, okay, you have to calculate it because ln will be different in this B2C2 case, and you got 132. So that why m naught, as this moment is less than this one, so okay, we don't need any adjustment. If let's say this moment is far away from this moment, so we will make adjustment, okay, and we will consider this moment. This kind of reduction governs when pattern loading is considered. Okay, this kind of situation may exist, may prevail when you are basically facing the load pattern. Although there are no load pattern, so that's why it's satisfied. This condition is satisfied. Clear? But it will only, you have to check this limitation only when you have the slab system which fulfill the requirement or the limitation of DDM method. This is extra limitation, okay, which I shared with you people. Now the rest of the things are same. You got, see in this figure, you have to find out the movement for this column, okay. Now at this face you see we got here 36 feet movement. So this movement and this 4 as well, it will be distributed to this column in view of its stiffness, as we did in example number lecture number 6, 7, I think so. So you have to do the same procedure as we did in those lectures, and you find the movement for this column, similarly for this column, and similarly for this column, which is the unbalanced movement. Okay, so at A2, 36 feet movement will be distributed between the top column in the ratio of their stiffnesses Kc, which is same for top and bottom column. So half movement will go to the top and half will go to the bottom. At B2, 0.80 feet will distributed, because you see in the table, where is the table? This table. You see at this B2 column there is a very little bit unbalanced movement, that is 0.80. Okay, so this movement will be distributed to the top and bottom column as well, and in that case it will also be distributed. Find out the lateral distribution coefficient used in the DDM method for flat slab, table 13.1 in Nielsen table, and distribute the moment laterally into middle strip and column strip, and then find out the amount of reinforcement. So as in this case we have no beams, so that's why we don't need to interpolate the values of alpha and beta. Okay, we don't need those things. We just need to find out this table and find out the distribution, lateral distribution coefficients. And one thing more, you don't need 0.65 and 0.35. okay, because the moment which we got here, okay, like you see here, these moments, you have to just distribute these moments laterally.
Now these are our longitudinal movements, remember. And remember, there are no beams, so these are the slab movements, and slab is, you can say, is responsible for taking these moments because we have no beams. So this why this example is different from that one. Okay, and you have to laterally distribute this moment, okay, similarly this moment. Now you have to pick the coefficients, and I think so I explained already these lectures in my DTM method, so please go there and watch. So I thoroughly explained these coefficients, how to use it, and how to distribute these longitudinal movements into column strip and middle strip, how to combine those movements, and how to design for those movements, and remember how to do detailing for those movements. So thoroughly explained. There are almost 15 to 14 lectures I have uploaded. There are in details, so that's why I'm not going in detail of those things because it just becomes the repetition of things. So my basic aim is that I have to share this example, okay, and how to cope with such a cantilever portion. Okay, this ends up this example, and in next, inshallah, I will search in another example and some different example. Okay, and if you people have any such kind of examples which you don't understand, you can share those examples with me, and I will help you. Okay, one thing more, students, basically this diagram is very important. Sometimes students may confuse. Let me show this step here. Sometime basically you see in this figure that the length of this column, or you can say the side, okay, of this column is if you look to the center line, okay, it is sometime there will be a concrete wall, or you can say a shear wall. So how much you have to take this distance from the center line? Okay, as for example, as you see, we calculate the face shear and the face movements. So there is some limitation of the ACI code which is explained right here. For example, if you have a shear wall, so C1 distance or the side of that shear wall, it should be greater than 0.35 L1 for a shear wall case, remember. And okay, and the face in such case, remember, the face in case of shear wall, as I already share one important diagram right here. Okay, this is important. You see here we have a shear wall. So in this shear wall, you have to calculate the face movement. Now you see this is the center line which is passing. Okay, now you have to, up to how much distance you have to consider the face of this shear wall. So basically it explains here that from the center you have to consider the face up to a distance of 0.175 L1. This is very, very important step. Now this is the face of the shear wall where you have to calculate your face moment. Okay, and let me, okay, in our previous example, okay, that is example number 1 by equivalent frame method, you see we have this column right here, but in that case our column is 14 inch and from the center it is 7 inch. The face of the column is 7 inch from the center line. So in that case our this distance is 4.375 feet. Okay, the face is located, or you can say the face movement can be calculated at this much distance, but we consider the face of the column that is at a distance of 7 inch. Okay, now let's say if you have a shear wall right here. Okay, so in that case your face will be located at this much distance, but you have to multiply that one with your L1, like you see in this picture. This is very important. Okay, like for example, if this is your from this column center line, this is your L1 distance, so you multiply 0.17 with that L1, you got the face from the center line for this shear wall, and similarly for this one. Okay, so this is very important step that I want to share with you people. Clear? And I think there is okay, interior support and exterior support with columns or walls. If you have a wall, if you have a column, okay, you have to do this, you have to follow this procedure. Clear? And instead of this, okay, if you have any question regarding your equivalent frame method, okay, you can ask. Thank you for watching. See you in next lecture.